Hi kids, this is Mr. Flamino. I'm going to be taking care of a little introduction to our last section in Chapter 4, 4-6, Exponential and Logarithmic Equations. This section is going to tie up all the loose ends, our last applications, and also give us the techniques for solving the equations that have previously been unsolvable to us. And what I mean by that is earlier we could not solve equations of the form 3 to the x equals 21 because we couldn't write them both sides of the equation using like bases. Use the definition of one-to-one to eliminate those like bases and get a solution from there. Maybe take a second here, try to think, how did we solve those equations up to this point? If I had some Jeopardy music right now, that would be good for you. But the answer is most of us probably solve this in a graphic method by graphing this under y sub 1, this under y sub 2, and performing an intersection on them. But what we are really interested in finding is an algebraic technique for being able to solve that equation. And through the last two sections, when we introduced logarithms and we learned the properties of logarithms, we now have enough knowledge and skill base to be able to solve this algebraically. So that's what this slide here says. Now that we've studied the properties of logarithms, we can solve this equation algebraically. So why don't we go ahead and tackle it? And to solve this algebraically hinges on using condition 2 of the definition of one-to-one. And we use that to do some solving, but it's a very powerful statement for us. And properly written, that statement says logarithm base b of x equals logarithm base b of y if and only if x equals y. And the variables might have been different from what your teacher used for that condition, but the idea is the same. And what I really want to highlight and put the importance on is that if and only if right there. Remember that if and only if allows a statement to work in both directions. Up to this point, we have been working with this condition in the left to right direction, where we've been using it to eliminate logarithms from an equation to make it solvable. Well, the truth is, in this particular case, we want to, that's not a very true, we want to use that condition in the other direction to create logarithms, which may be a little counterintuitive to think that creating logarithms is going to make an equation easier. Well, in this case, it actually makes it solvable. So why don't we go ahead here and actually go ahead and solve this equation. So if I have 3 to the x equals 21, and I'm going to say that is what I have on the right side of my statement. I'm going to say that I'm going to call that this 3 to the x is equivalent to this x over here in blue. And the 21 is equivalent to this y. So I've got my x equals y, and I'm going to use this condition 2 from right to left to create logarithms of base b. So I'm going to write logarithm base b of 3 to the x equals logarithm base b of 20. And the real truth is that choosing logarithm base b is not going to be helpful for us. We actually need a number in there, and a number that we can work with. In the previous sections, we've seen a couple of those. Base 10, our common logarithm, and base e, our natural logarithm. In this particular case, I'm going to choose logarithm base 10. That base b can be any base I want. I'm going to choose 10 simply because it'll be easy to work with. Now, if I look at the left side of my current equation, I see the 3 to the x is the input. We had a property last section that allows me to rewrite the left side of that equation as x times the common logarithm of 3. I'm not going to write the subscript of 10 here. We understand that to be a common logarithm. Equals the common logarithm of 21. So now I have x times the common logarithm of 3 equal to the common logarithm of 21. If I take both sides, divided by the common logarithm of 3, I will have x equals the common logarithm of 21 divided by the common logarithm of 3. Now, because I chose common logarithms, I can evaluate that statement on my calculator. When I evaluate that statement on my calculator, I get an approximate answer of, I'll make it approximate, 2.77. Which actually should make some good sense to us, because if I take a look at my original equation, 3 to the x equals 21. We know that 3 squared is 9. We know that 3 cubed is 27. So if we want 3 raised to some power to be 21, that power is going to be somewhere between 2 and 3, and we got 2.77. Just a note here, both of these last two lines are considered solutions. This line is considered an exact solution, and this line is considered an approximate solution. So pay attention to the needs of the problem. Whether you need an exact solution, you would leave your solution in terms of logarithms. If you only need an approximate solution, you go ahead, take that logarithm, evaluate it in the calculator, and get an answer. Right? So that is one way we can use logarithms to solve exponential equations, by using the condition 2 in reverse. Another way we could use this idea is to evaluate logarithms that might not have bases within our calculator. Some of us with the newer calculators can evaluate logarithm base 3 of 5, but some of us with the older TI-83s and 84s do not necessarily have that option. So how are we going to evaluate this expression if our calculators won't work? Well, we can use the same technique, a very similar technique to what we used in the last problem. What we're going to do here is I'm going to rewrite this logarithm base 3 of 5, and I'm going to set it equal to x. It doesn't really matter what it is, but I'm going to set it equal to x so that I can create an equation. I now have a logarithmic equation, which I can convert to exponential form. And now that we're looking at this, 3 to the x equals 5, you might be saying to yourself, well, structurally, it is very, very similar to the 3 to the x equals 21 we just did in the last problem, so we can just use the same technique. I can use condition 2 to create a logarithm on both sides. I'm going to choose the common logarithm again. Actually, you know what? I did common logarithms last time. I'm going to use the natural logarithm this time. So I'm going to take the natural logarithm on both sides. That's using condition 2 in the reverse direction. I will use a property of logarithms to rewrite the left side. I will divide both sides by the natural logarithm of 3, and I have an answer. Now I have to go to my calculator and evaluate the natural logarithm of 5 divided by the natural logarithm of 3, and I get 1.46 about, and that should make sense. 3 to the first, if I look at my original equation, we know that 3 to the first is going to be 5. 3 to the first is going to be 1, and 3 squared will be 9. So 3 to the x equals 5 is going to be somewhere between 1 and 2. And that is our value of x. Although we should clean up the notation, because we weren't asked for an x in our original equation. We were asked to simply evaluate this. We had just set that to equal to x. We had made a substitution. We really should give a final solution that says logarithm base 3 of 5 is equal to approximately approximately 1.46. Right? So that condition 2 is very, very helpful for us. Right? And we can generalize those sort of statements, and instead of going through that step the whole time, we can kind of generalize some of this into what we call the change of base formula. If I take this, if I have a logarithm of any base b of some value a, I can use the change, I can create this change of base formula, and it would be logarithm base c of a over logarithm base c of b. And remember that base c is going to be the base of your choosing, any choice you want. In the previous two problems, I chose a base of 10 in the first case. In the second case, I chose a base of e. And those are two ways of choosing those. We typically choose those because they're on the calculator, but once again, I'm going to remind you, it's not always the best choice to make. So why don't we go ahead here, and why don't we go through the details of where that red statement came from and look at it. And so I'm going to treat it just like we treat our last problem. I'm going to go with an x there. Go with an x there. I'm going to rewrite this as an exponential, b to the x equals a. I'm going to take a arbitrary logarithm, base c of both sides. Apply the property that allows me to take the exponent on the input and bring it out in front of the logarithm. So far, I'm doing the same thing that I did in the previous two examples, except instead of doing it with specific numbers, I am doing it in general case with just constants. I'm going to divide both sides by logarithm base c of b. And I'm almost there. All that's left to do is remember that I had set this x equal to logarithm base b of a, so I can undo that substitution. See it a little better. And so it'll be logarithm base b of a is equal to logarithm base c of a over logarithm base c of b. You know, and the important part here is to equate the parts that are equal to each other and get them all in the right place. And this final statement, the generalization of the techniques we've been using, this is what's called the change of base formula. And that change of base formula allows us to change the base of a logarithm to any equation, to any base that we want, depending on the equation we have and what might be easier. All right? So we've done a couple examples. We generalized. We got the change of base formula. When you come to class, your teacher will maybe review this for a few minutes, and we'll move on to actually applying this stuff in the center. I hope you found this helpful and useful. Refer back to it whenever you need to as you're studying and preparing for quizzes and stuff like that. Have a nice day.